So we're going to continue our discussion that we started last time of what hardware support is actually required for implementing an operating system. If you have a hardware platform that doesn't have all these things, then you're going to have a pretty weak operating system. And this is kind of why we're going to talk about MS-DOS, and I'm going to probably reminisce a little bit about all the naughty things we could do under MS-DOS, because it was fun. But the reason why MS-DOS sucked so much in that way is because the hardware support just wasn't there for creating a good operating system. And it wasn't until about the 286 or the 386 that we started being able to create real operating systems on that processor family. Other processors supported all of these things well before the x86 family of processors, so those operating systems didn't suck. But we kind of had some limitations because of what the hardware supported. So we had these components that we talked about, and we pretty much covered all of them. And we talked about how applications are not allowed to talk to the operating system directly. That was one of the characteristics of DOS, is that you could talk directly to the components of the operating system. You could modify them. You could create TSRs. You had all kinds of things you could do. So, but modern operating systems, we don't allow direct access. And of course, the code and the data that the OS manages are in kernel space and can only be executed in kernel mode. So we had that constraint. And the application code and data is in user space and it can be executed in user mode or kernel mode. So the question is, how does the application actually get into the OS? And we talk about this in CS24, so we don't have to spend too much time talking about it. But typically what happens is you execute an instruction that allows you to trap into the kernel. And almost always this is going to be some kind of software-generated interrupt that allows you to transfer from user mode into kernel mode so that you can now start executing kernel code and access kernel space data. So those are the details of how we get from the application into the kernel. And I mentioned faults here just because we'll go through all of that again just as a review. But remember, there's different kinds of interrupts. There's ones generated by hardware. There's ones generated by software, and different circumstances. They have different implementation details and different behaviors in the CPU. Remember that faults always go back to the instruction that generated the fault, because we may be able to retry it. Traps, on the other hand, and hardware interrupts go to the next instruction. So let's see, the OS initialization, the kernel sets up basically handlers for various kinds of interrupts, both hardware interrupts and software interrupts, so that when an application decides it needs to get into the kernel, it invokes the trap instruction, and then that causes the trap handler to be invoked. And the processor is going from one mode to another mode almost always. There's very few situations where a kernel would trap into itself. It's like, why would it do that? It can just call the handling code directly, so there's no real reason to. So like it says here, the processor can change into kernel mode. There's two benefits from doing this. One you may not think of so much, but it is nice to have a level of indirection between the application code that needs to invoke some operation and the operation being performed, because it may be that over time, as the OS is upgraded and code is added, code is removed, the addresses of these handlers are going to move. And so it doesn't make sense to have an address coded into an application. We need something indirect. So again, remember, indirection is our friend almost always. If we can introduce indirection, it gives us more power and capability. So having a trap handler, and of course, again, you probably all remember, int80 is the Linux and OS 10 trap handler, and on Windows they have like 2E, hex 2E or 25, I can't remember. There's a couple of different trap handlers used by various operating systems. And so it's like everybody knows that's how you get into the kernel. The kernel can structure the code however it wants. The other one is the more obvious benefit, which is that the operating system now has a controlled entry point, a single controlled entry point that can be hardened, and the operating system can make sure that there's no bugs in this, so that the application's requests and the arguments can always be evaluated. And we'll talk about this when we get to system calls. When I do a read operation, then I'm passing the kernel a pointer, and I'm asking the kernel to write data from a file into that pointer, the memory pointed to by that pointer. I may not be able to access it, but the kernel can access anything. So what if I give it a pointer to something in kernel space? Now I want the kernel to shoot itself in the head. So the kernel has to be clever, and it has to say, okay, thank you for this pointer. I'm going to verify that this is not a pointer that will cause harm. So, for example, it makes sure that it's in the address space of the user application. It's not in kernel space. That's one simple check that you'll have to implement for your system call implementation when we get to that point in Pintos. Simple example. Okay, so IA32 uses int. Let's kind of rush through this kind of stuff because who cares? We already talked about a lot of this stuff in CS24. But the different operating modes have different stacks on IA32, and this is not an uncommon approach. It basically allows the kernel to be insulated from the application. If you have an application that's behaving really badly, then you don't even use the application stack. You can use the kernel stack. And this interaction between kernel stacks and application stacks is actually pretty interesting, and we'll talk about it especially when we talk about how signals are delivered to applications. So arguments are typically passed in registers, and so you say what operation you want to perform. You also say here are the arguments. That obviously constrains the number of arguments you can have because you have a limited number of registers. And we had this example where I want to retrieve the process ID of the current process. And so I stick the value 20 into EAX. I invoke hexadecimal interrupt 80 or 128. And when the interrupt handler returns, the operating system has placed into EAX the process ID of the calling process. Okay? So that's a really simple example. We don't like to do it this way. We like to actually use the syscall wrappers that are given to us, but it's nice to understand exactly what's going on under the hood. Okay, let's see. Are there any questions about this at all? Any basic questions? So we're going to start diving into how it all works. All right. So IA32 has this big table, tabular data structure called the Interrupt Descriptor Table, which basically says this is the handler to invoke for each interrupt. And of course, since there's 256 interrupts, this table has 256 entries. And from 5X, you may be familiar with the interrupt vector table where we have 4-byte entries, but in protected mode, we actually have 8-byte entries because they have to have an address and they also have to have details about whether or not you're allowed to invoke this handler from a particular protection level, what protection level should you enter when you go into it, and so forth. There's a few other details that could be specified there as well. Okay? So you have some interesting details that have to be specified. So the interrupt descriptor table has larger entries. But they're all the same size, and so when you say int n, the processor does very simple computation, like shifts it at, left by 2 bits, 3 bits, something like that, some number of bits. And then it looks up the entry in the interrupt descriptor table and does a simple check. If the caller's at some protection level, then it transfers to the interrupt handler. Otherwise, it would probably generate some kind of fault that the interrupt is not allowed. Okay. Of course, most of the time, the way operating systems implement traps is they'll say you have to be at you can be at the lowest protection level, and we go into a high protection level to get into the trap handler. And then the trap handler can do its thing. When the handler is finished, it does the iret, and so that does the sequence of steps, basically getting back to the caller's privilege level. And the way that we set up this interrupt descriptor table is to use the LIDT instruction, and then that basically allows you to say this is where the interrupt descriptor table starts. So that's basically what we do there. Okay. Now, also, booting. We haven't talked about booting yet. We will a lot next week because it will be important for your second assignment. But it's really gross and it's grungy, and I'm apologizing right now, but I'm sorry, software has to run on hardware. So basically, when the IA32 processor starts, it starts in kernel mode. You're in ring 0 because you're in the operating system code. You need to set up the hardware. And so you need to be able to do all of these kinds of things. So basically, that's how you can go ahead and configure all of these things, and then you can later switch into user mode once the operating system is ready to start executing user applications. Okay, so that's basically the general idea of how we dispatch to these things. You'll see a very specific example of this, I'm pretty sure, in the second assignment, because I want you to be able to handle keyboard key presses. And the way to do that, obviously, is to set up a keyboard handler. So we'll explore that. Okay, exceptional control flow. So there's a lot of other operating system facilities that depend on exceptional control flow. Traps are the ones that we talked about, and of course then you have hardware interrupts. Okay, so we just generally call these interrupts. And basically you have a lot of long-running operations. I want to wait for network data to arrive, or I want to be informed when network data has arrived. I want to be informed when a disk performs some operation. Let me know that data is available, something like that. Or even timers, and we'll talk about timers a lot in a moment. Okay, faults, usually unintentional, but it is the mechanism by which we implement virtual memory and memory protections. So like I say, here's a potentially recoverable error. And so the fault handler tries to handle the fault and then goes back to the faulting instruction to try to execute it again. And if it succeeds, then yay. And if not, so another thing that you'll notice about this class is that there's a whole bunch of new ways to have infinite loops. And one of the ways is to have a faulting instruction where the fault handler doesn't resolve it, and then you go back and fault again, and I think you actually run into this in the virtual memory lab like right away. You run into faulting instructions. And you might have a loop that way. And then aborts are the non-recoverable hardware errors. Okay? So these are when I run into some situation and I do not trust that I can actually continue computing. These tend to be the kinds of things you see for aborts. IA32 does have one. It's called machine check. And I can't remember exactly what causes it to occur, but it basically causes your system to halt. Okay? Let's see. Now, other ones that will be more relevant to you as we get into assignments 3 through 6 are ones that are... They typically indicate operating system bugs. So you have a double fault abort. And the scenario basically goes like this. You have an interrupt that occurs, and that's all fine. You know, this is all normal operation. And so the CPU looks up in the interrupt descriptor table, what handler do I want to invoke to execute or to handle this interrupt? And so the CPU tries to invoke the handler, and in the process of invoking it, we get another issue, typically as a fault. So let's say that the handler is not in the address space, or it's not allowed to be executed because there's a protection level issue. You could have a number of other things that could occur as well. But we basically have a fault in the process of dispatching an interrupt. So that's a double fault. Okay? Now here's another one that causes a double fault. And this one, again, is one that you will probably see at some point. So you have a user program that triggers a page fault, and then in dispatching the page fault handler generates a page fault. Okay? Because if you think about it, what is supposed to be used to resolve the page fault? The page fault handler. So if invoking the page fault handler generates a page fault, you're done. Game over. Okay? So these, you can see, are generally caused by operating system bugs. Now you can register a double fault handler, which is kind of nice. If I remember correctly, I can't remember exactly how this is all done in Pintos, but we'll remember very quickly when we get into those assignments. But I believe that Pintos has something set up so that you can actually like trigger GDB or something like that when you get into a double fault or a triple fault situation, so that you can say, okay, yeah, things are going bad fast, so let's get into the debugger and see exactly what's going on. So you can register a double fault handler if you wish. Although generally what this would do is try to recover the operating system to a point where it can continue executing. So you try to limp back to life if you possibly can. Linux has a really interesting mechanism for trying to deal with kernel bugs, which we'll talk about when we get into system calls. So basically the amount of times that you see a kernel panic should be relatively infrequent because it can actually recover from a significant number of issues. Okay. Now, let's say that it tries to invoke the double fault handler, and that also generates a fault. Okay. Then you get a triple fault, and don't worry, we don't have quadruple faults and quintuple faults and so forth. Basically, the CPU gives up when we see a triple fault. Okay. What happens is basically either the system resets itself, it basically does a hardware reset, or it waits for a user to do a hardware reset, or in rare situations, like if you're on a multi-core system, you can have one core try to reset another core. Because obviously all of this is occurring in, it's an interaction between software and hardware, but it's an execution path. So if you have multiple cores, you might have one core that's flipping out and another core can try to reset it. Okay? So I just want to point this out when we talk about interrupts, because it's not uncommon to see these in CS124. And again, another kind of infinite loop. You have code that triple faults, you see your system reboot, then it tries to stand up and it triple faults again and it reboots again. So if you ever see your operating system just rebooting over and over and over again, have fun. That's the issue there. Okay? Any questions? All right. So, hardware interrupts. So certain kinds of multitasking, we require hardware interrupts. We also require another facility that we're going to talk about now. So simple operating systems will use cooperative multitasking. It's kind of a very easy way to stand up a multitasking system is to have cooperative multitasking. You rely on processes to either voluntarily release the CPU or do any long-running operation, because typically the long-running operation also informally relinquishes the CPU. So, for example, if you ever, I don't know, again, you guys are getting so young. I started teaching when I was 29, and so this kind of stuff happened all the time. But now that I'm 40, it's like probably none of you have written Windows 95 code or pre-Windows 95 code. Definitely, I would guess. Nobody's written like Windows 3.1, Windows 4 code. So, but you're talking now, or pre-OS 10 code as well. You're talking about operating systems that actually implemented cooperative multitasking. And most of the time you didn't actually think about it. But if you wrote a program that did I.O., then you were implicitly cooperating, because when you would do an I.O. operation, the operating system would make you release the processor. Okay? But if you just did a compute-intensive thing, you could cause the whole operating system to halt or seize up. Okay, so but basically the processes were required to be good citizens in these kinds of systems. And of course, this is a bad assumption to make. It's very easy to write a broken program, it turns out. Or it's easy to write a broken driver. And that was frequently what would happen, is you would have drivers that misbehaved. And so when the program called into a driver, it would cause the operating system to fail. Nonetheless, you had a number of operating systems that basically only did cooperative multitasking for a surprisingly long time. So all Windows operating systems up to Windows 95 actually were cooperative. And Mac OS before OS 10 was actually cooperative. It did cooperative multitasking. And then there were a lot of other older operating systems that did cooperative multitasking. Interestingly, the exception, UNIX variants, remember that UNIX was designed for mainframe computers and mini computers and things like that. So we're talking about large systems where we couldn't keep them maxed out unless we supported some kind of multitasking. So UNIX variants pretty much supported multitasking and preemptive multitasking all the way along. It was only these desktop systems where you had a single user and there wasn't really heavy multitasking requirements that you could rely on cooperative multitasking. So, of course, the solution to badly behaved programs in the context of cooperative multitasking is to preempt them sometimes. And the way that we preempt them, you drive the preemption by introducing a hardware timer. So the OS configures the timer. It says, I want you to get back to me in, let's say, 10 milliseconds. And then you go ahead and turn over execution. You turn over the processor resource to the program. And the program executes. And if the program doesn't do anything that requires kernel intervention, then the timer goes off and it can intervene and switch to another process. So this allows us to do preemption now. Okay. Let's see. If you want to do this kind of thing, you have to have a timer that is only configurable in protected mode. Because if you don't, then an application could just get on there and say, hey, I'd like the timer for like ever. Never trigger. And then the program gets to have the CPU forever. So the operating system has to have a way of saying the timer can only be configured by me, and then you have an operating system that's pretty bulletproof at that point. Okay? Let's see. Yeah, and so all of our operating systems now that we use have preemption. Thankfully, people have gotten a clue and implemented things in a clever way. And as I said before, all the UNIX variants basically had preemption from day one, so that wasn't something they needed to add. Okay? So, any questions so far? Just to talk a little bit about how this is implemented, there's a particular component on your Intel PC system or x86 based system called the Advanced Programmable Interrupt Controller, or APIC. Okay? People frequently call it just the APIC. And basically it allows you to configure your interrupt handling in a lot of different contexts. It's a very powerful component of your system. There's a lot of different sources that it can receive interrupts from, and so the APIC has as well several different components. You have the local APIC, which is sort of close to the processor proper, or the core itself, and that'll handle things like interrupts that can occur, hardware interrupts, and then also local I/O operations that may occur. And like I say, your timer-generated interrupts, thermal sensor interrupts. Hey, your processor is 980 degrees. You should probably stop it or slow down the CPU clock, things like that. A few other details as well can be configured on the local APIC. And yeah, so I'll talk a little bit more about that in the future. There's also an I/O APIC, and that basically lives on the motherboard and allows you to configure things like disks and keyboards and so forth, so that those things can be delivered to the processor as well. Okay, so you may have noticed, like on Bootstrap, especially if you don't use a Mac, if you use a PC and you happen to be from the BIOS days as opposed to the UEFI days, and we'll talk about what those things are next week. But you'll sometimes see interrupts assigned to devices. You might see that in the text right at the beginning of boot up, and that's where the I/O APIC is being configured so that the operating system can say, okay, this device is mapped through this interrupt into the processor, so the operating system can know what interrupt that certain things will occur on. Okay. Other details, like I say here, different devices can have prioritized interrupts, so that if two of them occur at the same time, which one is delivered? I should say which one is delivered first. So those kinds of things can be set up. All right, so yeah, the I/O APIC usually lives on the motherboard. Now, if you have a multi-core system, then it gets a little bit more interesting, and this is honestly one of the more fascinating aspects of multi-core operating system development, is figuring out how to get all the processors to play well together. If the local APIC no longer gets interrupts that are I/O interrupts, it now only gets APIC interrupts, and it starts getting its I/O interrupts from the I/O APIC. And then all the processors share an APIC bus that allows these components to communicate with each other. Okay. Why might that be? Well, you have a couple choices. You can either round-robin interrupt delivery so that no processor is stuck always being interrupted in what it's doing all the time, and that way you kind of spread out the load. It kind of is a good way of reducing interrupt latency, or the average interrupt latency, by spreading out interrupts. But there's an interesting issue that if you have all the processors handling interrupts, then the caches fill up with the interrupt handler code, and it takes away from application code and so forth. So sometimes people like to put all the interrupt handling on one processor. So there's different ways that the operating system can configure it, and so that's one of the example details of what the how the APIC can be configured. Okay, I want to set up where interrupts are delivered. Do I want it to be round robin? Do I always want it to be a specific processor, and so forth? Processors can also use this APIC bus to communicate with each other. So every local APIC has an ID. You can actually use, I can't remember if it's a CPU ID instruction or CPU info instruction, or if there's somewhere else that you get this information from. It's been, I think, a year or two since I looked at this. But you can look at the APIC IDs, you can retrieve them in software, and then you can use that to cause an interrupt on a specific core. So like it says here, IPI, those are inter-processor interrupts. And so you can say, hey, everybody, wake up. Or you can say, hey, everybody else, wake up. Or you can say, hey, so-and-so, I need your attention. And so imagine that you have a program that's running out of control. And it's running on a different core, and you'd like to kill it. Well, then your core can signal the other core, cause the operating system to start running on that core, and then it can step in and interrupt the or kill the process. So there's various mechanisms that you can interrupt, that you can use for causing these cores to communicate or collaborate with each other to carry out OS facilities. Okay, any questions? All right, so that's that. Yeah, hardware interrupts also for long-running I/O operations. So again, this is just covering how all we use these interrupts, this interrupt facility. We had this example from CS24, and it's going to be pretty important to you in your command shells because you'll actually have to use read and you'll have to use write. Or maybe you won't directly, but at least you can look at the utility programs that I provided and see how they are used. It's really straightforward. You just read a bunch of data into a byte buffer or whatever, write it back out. So I want to perform a disk operation that's slow, so the operating system sets this up, tells the disk controller, interrupt me when it's finished, and then it can put that process in a queue saying this person's blocked on this disk, and then it can switch to another process. Okay. So you can see that interrupts are very important for being able to maximize the utilization of the processor. Okay. So these are the hardware requirements of modern operating systems. So we can just sort of review this real quickly. At least dual mode execution. So I have to have user mode and kernel mode. I have to have some facility for specifying process address spaces and process isolation. Okay, so I have, and also like I say, protection from the operating system, between operating system and applications. I have to have the ability to trap into the kernel. If I have isolation and protection set up, then I have to have a way of getting in. So that's the trap mechanism. I have to have software interrupts and hardware interrupts so that I can implement preemption. And I can also have devices interrupt me when they're ready so that I can have an efficient operating system. And then the hardware timer facility allows me to implement preemption as well. Okay? These are all the things that are required for modern operating systems. Any questions? Okay, so that's that. Yeah, and we're going to dive into a lot of this stuff. Obviously we'll talk about dual mode execution when we get into system calls. We'll talk about, you'll run into the hardware timer right away when we get into Pintos because you'll have to add some facilities for kernel threads and so forth. And thankfully you don't have to talk to devices directly in Pintos. But you will have to think about virtual memory management, so that'll be another place where you see a lot of this stuff. So we'll talk about these facilities as we need them. So the next thing that I want to talk about is, and we'll take a couple of lectures to cover this, is basically the common structural patterns for operating system implementation, OS architecture. So the number one thing that you'll notice is this, it's called separation of policy and mechanism. Again, just like anything, we have a separation of concerns, but specifically in operating systems, you frequently have a choice of what needs to be done and how do you actually do it. And you do not want to combine those things in the same place because it's just ugly, and it turns out that one of these things changes all the time and the other one doesn't change very often. So like I say, your policy says what needs to be done. And the examples here are virtual memory paging and process scheduling. Really good examples of things that have different policies, many different policies that you can choose. And then the mechanism says, how do I actually do that thing? So virtual memory pages. I need to evict page so-and-so. Okay, how do I actually save it? What do I do to the page table? Those kinds of questions. Okay. When I have a process that should be run next, okay, so it picks which process should run next. Now I need to save the current process's context, I need to do the context switch, and I need to restore the next process's context. That's mechanism. How do I actually implement that changeover? The way that these operating systems work is that almost always the mechanisms rarely change at all. You obviously see differences from OS to OS, but within an OS, the mechanisms change very little. And with a given set of hardware, obviously it's going to change very little as well. So the mechanisms basically don't change very much. But the policies may change so often that they are even part of the operating system configuration. Okay? How many people have Android devices? Yeah, I have an iPhone now. I used to have an Android phone. How many have heard of the governor on Android? Yeah, a few of you. So the governor is a component that chooses what clock speed should your phone run at. And obviously, you want a governor to decide that, because if you always ran it at the maximum speed, your battery would last probably like 40 minutes, and then you'd be sad. And if it always ran at the slowest speed, then your phone would be unresponsive and you'd be sad. So the governor chooses how to control the CPU clock. And there's many governors you can install on Android. If you have your phone rooted or you have root access on it, you can easily configure that. How you actually control the CPU speed itself is obviously mechanism. So that's outside of the governor. The governor specifies the policy. Okay, so operating systems can follow various structural patterns. There is a structural pattern which is not a structural pattern, which is the simple structure, which kind of means big ball of mud. Okay? So there's no clean division into modules. Every part of the OS can access every other part. It's really fun. It's, you know, either Wild West or Steel Cage Deathmatch, pick your analogy. And basically everything can also access the computer hardware. And it usually happens when OS development happens incrementally without careful upfront design. Okay? And there's quite a few example OSs which fit this design pattern, actually. So problems are pretty obvious. You have a lot of issues related to bugs. An OS bug can make it really easy to break everything. Application bugs can bring down the operating system. I'm serious. The example that we're going to talk about for the simple structure pattern is MS-DOS. And it was very easy for an application to bring down the entire computer because the operating system was very light and very limited in its capabilities. Okay? So, and like I say here also, when you have something that's not well structured or well architected, it becomes very easy to extend the OS's functionality at some point. So MS-DOS, there's a part of the reason why MS-DOS is so I have to be careful how I say that. I don't want to just bash on it because I actually really enjoyed using it when I was a kid. But part of the reason why MS-DOS was so limited is because of the processors that it ran on were also limited. There was no protected mode execution. And basically, this is how it worked. You had the computer hardware, which you could use ROM BIOS calls to get into the computer hardware. I want to change to we didn't even have VGA necessarily back then. So you would have, like, I want to do 4-bit, CGA color. You had 4 colors. It was great. I want to have device drivers. They may call into the BIOS. They may access hardware directly. They would somehow be installed in memory. Then you had resident system programs that could access any of these layers, or they could talk to the hardware directly. And then applications, which could talk to any of the layers or the hardware directly. It was fun. You could do anything you wanted to, which is also why it was scary. Okay? So you had computer games that would talk directly to the computer hardware and put the graphics cards into graphics modes you've probably never even heard of. Okay? There was a thing called Mode X, which was very popular for early computer games. The computer video hardware was set up to be very optimized, and you could do some really clever stuff, and it was pretty neat. No 3D acceleration at all. You could also have libraries, like extended memory libraries. It was really common that you needed to get some library to allow you to access the full megabyte of memory or something like that, because usually you'd start out with 640 kilobytes, and then you had to do special things to get to the full megabyte, and then if you wanted multiple megabytes of memory, forget about it. You had to do some really crazy stuff to get that stuff. Also, malicious programs, which I certainly had a lot of fun exploring many different kinds of malicious programs, because I had a real interest in computer viruses back then. And there were certain kinds of viruses that would be able to basically, the interrupt vector table is in the first part of memory, and anybody could write to it. And so you could just capture all interrupts coming through, because int21 was the DOS interrupt, or you could intercept. You could intercept any of the BIOS interrupts as well, and you could basically change the way they behaved. And so a lot of times what these stealth viruses would do is they would cut out a little bit of memory at the top of the address space, the 640 kilobytes. They'd put themselves there. They would redirect DOS interrupts into their code so that they could handle them, and then they would delegate out to DOS when they needed to, or delegate out to BIOS. And then when you had calls that would say, how much memory is available? Or, I want to open this file. Well, they would all go through the stealth virus, so they could just pretend like everything was exactly the way it was before. It was really clever. Really dastardly, too. So it was quite interesting. This was part of what got me interested in this low-level system stuff in the first place. All the things that you see stealth viruses do, which is not possible now, by the way, given how the hardware works. Okay, now Unix, a little bit better than DOS. They actually thought more carefully about this stuff, and I think, again, it was because they had systems that were used by a lot of people concurrently. And so you did have this division between applications and the kernel, and you did have system calls and so forth. The kernel itself, I have all these pretty boxes below the system calls, and that wasn't the way it was initially. It was all kind of, again, simple. Everything was together. But then over time, they developed more structure, at least from a software engineering standpoint, but it was still all in the kernel. It was all still in kernel mode. And so this approach is called a monolithic kernel because the kernel contains a lot of things. Okay? And it is still possible because if you have all of this code running in kernel mode, it's really easy to have one bad bit of code compromise the entire operating system. Okay, kernel subsystems can access each other. And again, when you study Linux, Linux is a monolithic kernel, and it's very common that you see this part of Linux, this part of the Linux kernel talks to this other part of the Linux kernel. It just accesses stuff directly, because it's all monolithic. It's all part of the same large thing. Okay? The reason why people do it is because it's amazingly fast. Okay, remember the things that are slow. Context switches are slow. Trapping into the kernel is not the fastest. We like to avoid doing it if we possibly can. So those operations are slow. If I have everything in kernel mode, and it's in kernel space, and I need to access this part of the system, just access it directly. So it's super fast. And this is the reason why monolithic kernels are still so popular. In fact, we'll talk about it next week, but there was a certain version of Windows where Microsoft tried to move to a more microkernel-based architecture, where you actually have very small kernel and a lot of stuff living in user space. It was too slow. And so they started moving stuff back into the kernel so that now it has a monolithic kernel as well. Same thing with the operating system that Mac OS X is based on. It's, probably you've heard of Mach if you dug into Mac OS at all. And the Mach kernel started out as being a microkernel architecture as well. And it ended up being monolithic as well because it was just too slow. Okay? So that's the reason why people use monolithic kernels so much. Okay, so monolithic operating systems still bug-prone, still have a lot of concerns about the stability and reliability of monolithic operating systems. So basically, one of the approaches that was explored was called a layered structure. And this was actually devised and pursued by Edgar Dijkstra. So he actually spent some time exploring this. And basically, each layer is separate from the layers below it. Okay, so it only talks to the layer below it, immediately below it, and it exposes some operations to the layer above it. So the layer is basically an encapsulation within the operating system. And so the higher layer really only talks to the layer immediately below it. Unless, of course, you have something where you need to go a couple of layers down, and in that case you might do that, but it tends to be infrequent. Okay? And like I say here, it really only cares about the abstractions, not the implementation details. And the idea is you start building at the bottom, and when you start building the next layer, you test the crap out of the layer below it. And it allows you to create a whole bunch of tests, and so that you can sort of verify that these layers work well as you build up the structure. And so there's an OS called the OS, and so how do you refer to it? Well, it's the OS. And this was actually an operating system. It stands for, I can't even pronounce that, Technische Hochschule Eindhoven. I actually know somebody who could pronounce that, but I didn't bother to ask them before doing this. But it's basically the Eindhoven University of Technology or something like that. That's basically what it means. So it's the Eindhoven equivalent to Caltech. And basically it was a batch processing system. So it was running on mainframes. So it was actually pretty simple back then. And they had 6 layers. And each layer only interacted with the layer below it. And so Dijkstra actually started at layer 0 because he's a computer scientist. And layer 1 would interact with layer 0, layer 2 would interact with layer 1, layer 0 interacted with hardware, and so forth. Okay? And each layer was tested. So when you're testing layer I, well, you have to have started building layer I plus 1, or else you can't have code to test layer I. So you just sort of are slowly building up the layers. And it's funny because you have to remember this was on a batch processing system that they were running it. So you have your stack of punch cards or you have your tape and you have to study the code because it may be a while before you actually find out if your thing worked properly. So they spent a lot of time thinking about what tests they needed to execute. They thought a lot about the test code, the code that was being tested. They thought about all these things. So it was a very methodical process, much more methodical than we have now, where it's just like, oh, I'll bang out a bunch of code, and then I'll bang out a bunch of tests, or maybe in the other direction, depending on your strategy, and then you run it, and it's like, okay, it didn't work. Well, I'll try it again, try it again, try it again. This was very, very methodical because of the context at the time. So layer 0, multi-programming. CPU scheduler, so now I have multiple tasks that I can execute. I have hardware synchronization mechanisms and so forth, or I should say hardware-based synchronization mechanisms, because it's actually possible to build synchronization entirely in software on your processor, which is kind of clever. We'll talk about some of those algorithms in a couple of weeks. But yeah, interrupt handling and so forth. Layer 1 was the virtual memory system and the pager, which is obviously an important part of virtual memory. Layer 2, OS communication to the console. Layer 3 is device I/O, including buffering. So layer 2 didn't really have any buffering. Layer 3 does. And then layer 4 is user programs, which was easy because the THE operating system didn't have a lot of applications to implement. It only had 5. I need to be able to build software, I need to be able to run software, and I need to be able to print. So not very complicated. They didn't have like, I don't know, a media player or anything like that. And then layer 5 was the operator or users. And Dijkstra famously says in his description, not implemented by us. So I guess he's begging off the testing aspect of the operator. But you can see how each layer just interacts with the previous layers, and you can test it very easily. What they ended up with was an operating system that was incredibly reliable and very few bugs, and the bugs that they ran into were really easy to figure out and solve, which is really nice. You'd think, okay, well, that suggests a good approach to operating system implementation. But what they found is that it took a long time to get to the final OS. And really what it was is they spent a lot of upfront time designing, and then implementation was very slow and very methodical, but they ended up with something really high quality. Okay? And so it's one of those things where it's a risk that companies frequently aren't willing to take. Like I say, why don't we use this? Well, oftentimes, it's especially with managers that aren't very experienced with software engineering, they see design as not work and implementation as work. Oh, you're coding? Good, we're making our progress toward the goal. Well, that may in fact be you're making progress, but maybe away from the goal. So, it's kind of a sad thing that companies don't take advantage of this more. One issue, though, is that layered approaches, you have things implemented as APIs and calls between APIs, even if it's all within the kernel. So you're not trapping into the kernel or anything like that. You still have calls that you're making. Well, that takes up time. Okay? And so you may have multiple call sequences that you have to go through to perform simple operations, and so that would slow down the operating system performance. Okay, so you can always make fewer layers that are fatter, and then the fatter layer is probably going to be harder to test and harder to debug, but it'll be faster. You can see how there's this trade-off between performance and reliability, which is kind of disturbing. We'll see it even more next lecture when we start talking about microkernels. Okay? Any questions about layered structures? Okay, the last thing that I want to talk about today is modular kernels. Because again, if you're familiar with Linux, you've probably heard that the Linux kernel is a modular kernel, It's a monolithic kernel. What does that mean? Which one is it? Well, it turns out that it's actually both. Okay? So monolithic kernels can definitely have extensibility issues because the kernel is all your operating system code that talks to peripherals, talks to itself, and then provides system calls to the application. So we'd like to support a lot of different devices. And like I say, if you wanted to add a new device to a monolithic operating system, what you would do is you'd write the device driver, and then you'd compile it into the monolithic kernel, so now it's in the kernel, and then you go ahead and load it and run your kernel. You have a couple of issues from this. One is that the kernel becomes ginormous because you have to have compiled in support for a lot of different devices, especially in the Intel PC world where you can plug whatever hardware you want into your computer, and then ideally the kernel will already have support for it. Okay? So, and like I say here, more code means more bugs, which makes the kernel less reliable. So that's not good. Just to sort of mention a few things about this. See, back when I was an undergrad, and you would get Linux on a stack of 3.5-inch floppies about this tall if you wanted a complete distribution. Maybe you were lucky and it would only be about this tall if you just wanted the limited parts of the operating system. And then, you want to install Linux, you would be the operator slapping 3.5-inch disks into the computer as it's loading up all of the stuff. It was a different world, and typically the kernels started out having everything compiled in because we didn't have this loadable kernel module thing really very popular or very widespread. And so one of the steps that most advanced Linux users would go through is you start up a particular, I don't even remember the commands off the top of my head. I wish I could. It's like all the stuff I used to have to do. But you'd start up the Linux kernel configurator, and you'd figure out which modules you wanted to include or exclude, and then you would rebuild the kernel, and then you'd reinstall the kernel, and then you'd restart your computer and hope it came back, because if it didn't, you were really in trouble. Get the stack of 3.5s again. And so that's how you would actually set up your computer, because you would want to compile out the stuff you didn't need so your kernel wasn't gimongous. Okay? We don't do that anymore. We don't have to do that anymore because we now have loadable kernel modules. Okay? And so if you have loadable kernel modules, you say that your kernel is modular. It's still monolithic, but it's now a lot more, it's a lot simpler to incorporate or to exclude different pieces of the kernel. Okay, so like I say, there's certain core services that are always compiled in, but there's also interfaces defined internally. So it does facilitate internal structure to have a modular kernel. So if you have things like block devices that I might want to support, storage devices, different networking devices, different other peripherals, then I have basically interfaces inside the kernel that can be specified, and then drivers can go ahead and implement those things. Now I have a new module. Well, how do I get that into the kernel? Who here has done like insmod and lsmod and okay, you guys are going to have to, at the end of this class, all of you had better have tried these things seriously. It's like basic, well, it's not basic, it's more intermediate, but it's really cool and important stuff. Basically, there's a module loader that knows how to link modules into your kernel. And what it does is it actually statically links that module code into the kernel. So the module lists symbols, the module lists symbols that it needs, the kernel has symbols that are exposed, and so that thing is actually linked into the kernel. Which, I mean, it's crazy. You have a file of module code, and it's being linked into kernel space so that it can now access the rest of the kernel. You better trust your module. Okay? And like I say here, there's various facilities for unloading them and so forth. I think I talk about this in a lecture toward the end of the class. Okay. So basically, you get the same high performance of monolithic kernels. Modules can encapsulate some of their state by controlling what symbols they actually expose. And you can end up with a monolithic kernel that's a lot smaller because you only load the parts of it that you need. And operating systems are pretty clever. They know how to dynamically load modules based on what is necessary. Again, when you boot Linux, you notice some of those things. Okay, I'm probing for devices. Oh, you've got this device. Okay, I'm going to load this module that knows how to talk to that device. It just does all of it automatically for you. We had to do that manually back when I was an undergrad. Now, the drawback is you really only slightly reduce reliability because you still have these kernel modules that can talk to any part of the kernel. Like I can have a printer driver that messes with the process scheduler. That seems bad. But so you can still have modules that can bring down the entire operating system. So it's pretty bad. And so like I said, modules basically reference and expose symbols that are global within the kernel. So basically, you have a slight improvement in the structuring of the operating system kernel, but not a huge improvement. And you have a slight improvement in reliability, but not a huge improvement. And so modular kernels, very valuable, very important, very common now, but really they don't get a lot of improvement over, sort of basic pure monolithic kernels. Okay, any questions about that? Okay, so we've talked about basically all the ugly things. So yeah, this is basically a few details. Oh yeah, so monolithic kernel, just as one last little note, monolithic just means how much code is running in kernel mode. And in a monolithic kernel, you're running a lot of stuff in kernel mode that doesn't strictly need to be there. Okay? And that will be important when we start talking about microkernels. Okay, so next time we'll go ahead and continue this discussion of OS design patterns and wrap that up next time.